Today we want to bring some ideas together when we talk about and do that through parameterizing a surface. So if you would recall, we have a function y equals f of x. We have a one-dimensional curve in R2, a one-dimensional curve in two-dimensional space. And when we have a function of two variables, although we didn't call them y. It doesn't really matter, but let's do the standard thing. Z we have z equals f of x, y. We'll end up with a two-dimensional surface in R3, three-dimensional space. The reason for the space that we're sitting in is just the number of variables that we put into play. So R2, because we're just describing a bunch of points, x, y. All the points in R2 look like x, y. And z equals f of x, y will have to be something in R3 because I've named an x, a y, and a z. When we're making a function, when one variable is a function of the other variable or variables, we're taking the dimension of the space and subtracting one. And then that's what the dimension of the thing that we end up with. So we end up with a one-dimensional curve in R2 because we've got one input. Z equals f of x, y ended up producing a two-dimensional surface in R3 because we had two inputs, an x and a y. This carries into our other descriptions of curves in R2 and surfaces in R3. If we make an equation relating x and y, that's one step up from y being a function of x. If we remove that restriction, if we think about an equation in x and y, an equation in x and y will give us a one-dimensional curve in R2. R2, because the only variables I put in play are x and y. And I made a relationship between the two, and I end up with a curve. So for example, x squared plus y squared equals 9. It's going to be a circle in R2. This is a bit more general than our function. We know that we can't take our circle and express it as one function. We have to write two functions. But this equation involving the variables in our space produced a thing that was one dimension less than our space. The same thing happens if I put in another variable. If I write an equation involving x, y, and z, we'll produce a two-dimensional, we will be describing a two-dimensional surface in three-dimensional space. Three-dimensional space because x, y, and z. Two-dimensional surface because I've got an equation involving all three. And this is a generalization of the stuff that we were doing in the previous, where we were writing one variable as a function of the other variables. Our most restrictive category is function. Second, one up from that is just writing an equation where we don't need a function, but we see the same stuff the same stuff applies. R2, because we're dealing with x points x, y. Sentences are difficult today. R3, because x, y, and z. This equation business drops one dimension out of it because I'm looking at a relationship between the two variables. There are certain things that equations can do that functions cannot do, but there are certain things that certain curves in R2 or R3 that we might not be able to express with an equation or a function. And for that, we introduced the idea of parametric equations. If you're thinking, dude, this lead into parametric equations seems like the same lead in we did to parametric equations already. Didn't we already do this? And I'm like, oh, yeah, because everything is the same. I just select a track and hit play. That's all I ever do now. That's what happens after you've been teaching for 20 plus years. You just build up a track list, a Spotify playlist of shit that you say, and then hit play. Happens at parties too. People that know me realize that the last thing that they want to hear when they're at a party that I'm in attendance, like, oh, so you're a math teacher? What do you do? I teach calculus mostly. Oh, what's calculus? Then all my friends just immediately leave the room. It's like, oh shit, they just hit play on Leach's playlist for calculus. He's going to talk about that infinity bullshit. Oh man, I'm just getting out of here. And meanwhile, the person, the hapless fool that just asked me what calculus is like, uh-oh, I think I'm in trouble. And usually I just say right out loud, it's like, oh yeah, you are. Why don't you have a seat? This is going to take a while. They're like, well, how long? 17 weeks, 3 times. And I go, oh, what did I do? Can I just walk away? Oh, yeah, totally. You probably should. It's great. No one talks to me at parties. It's perfect. Anyway, what are we talking about? And right now, all of you are like, oh, wait a second. Is that an option for me? I'm in your class, but could I have just walked away at any point? I'm like, oh, yeah, totally. Because I decided to treat you like adults. Remember, there are like 40 people enrolled in this class, and only 10 of them are showing up any day. Because like, look at all the people that are like 9 people, 8 people logged in today, which is low. Normally there's more people logged in on Zoom, right? Sometimes the number of people logging in on Zoom outnumbers the people physically in the class. And then the number of people logged in on Zoom might not actually be there. Because I could be like, 10 points for putting F in the chat. And not everybody would do it, right? It'd be like the easiest 10 points. There we go. So anyway, I can respect that maneuver. Parametric, now everybody's going to do it. It's like, I don't want to take any chances. F in chat. All right. So yeah, we just hit play on this thing again, but we want to point out something different about it today. It's like when you watch a movie a second time, so like don't be complaining about this. When you watch a movie, if you watched a movie more than once, you watch a movie second time, you come at it with a different mindset. The first time through, you miss all the stuff. But the second time through a movie, you pick up more stuff that the movie was trying to do. So we got to pick up some more stuff that this movie is trying to do. With parametric equations, we're trying to describe, we initially wanted to deal with parametric equations by saying, we want to describe a one-dimensional curve in three-dimensional space. That was kind of our goal, right? But for parametric equations, we can define one-dimensional curves in R2 and R3. That was the big advance in this technology. We can now describe a one-dimensional curve, not just in R2 with some equation or some function. We can also describe a one-dimensional curve in R3 by writing each coordinate as a function of some parameter that sits outside of the space. So for R2, we just define x of t and a y of t. And for R3, we just define a z of t. Our parameter doesn't have to come from a closed interval. It's just that we often did because we wanted to integrate things. We're defining the coordinates as functions of some parameter that's sitting outside of our space. That's the important thing. R2 is still just x and y. R3 is still just x, y, and z. T is sitting outside of our coordinates. So we define our coordinates as functions of a parameter. We define the coordinates as functions of some parameter, and that parameter is not one of our coordinates. That's what allows us to do stuff with parametric equations that we can't do with equations and functions. So the parametric equations that we've done work with so far, we wanted to describe a one-dimensional curve specifically in R3, but we started off by describing them in R2 because this stuff is backwards compatible. So we want to think about where the R2 and the R3 come from. R2, because we have X and Y. R3, because X, Y, and Z. The parameter T is sitting outside of that. The X, the Y, or the X, the Y, and the Z are all functions of the parameter that is not one of our coordinates. Here are our coordinates, X, Y, and Z. T is not one of those coordinates. It's the parameter in our function. And in this case, we're describing a one-dimensional curve in R2 and R3. So this one-dimensional curve part goes back to what we had up here. Y equals f of x is a one-dimensional curve because we had one input, and we had a two-dimensional surface when we had two inputs. So the reason that we're getting one-dimensional curves when we parameterize x of t, y of t, and z of t is that we're dealing with one input. So this one-dimensional business is still because we have one input. We have one parameter. So if we want to parameterize a surface, we'll just use two parameters. We have two parameters that'll produce a two-dimensional surface. Well, actually, that would be kind of silly, because if we describe a two-dimensional surface in R2, then we'll just have R2. So let's just describe a two-dimensional surface in R3. Since we're doing something in R3, I need to describe a bunch of coordinates that are x, y, and z. If we're going to make a two-dimensional surface in R3, we'll need two parameters. If I recall correctly, the Hughes Howlett text uses S and T as our parameters. So we're going to describe our surface. All that the surface is a bunch of coordinates, and we're just trying to organize how we describe all those coordinates. So x will be a function of s and t, y will be a function of s and t, and z can be a function of s and t. Let's think back to our simplest surface, a plane in R3. We can describe a plane in R3 with a function I know at this point saying a function and an equation, they're the same thing. A function is describing things with an equation, but it's a particular kind of equation. And since the plane can be described as a function, it's kind of weird to talk about the function and the equation, but I'm going to write different forms. So in this case, it's just going to be different forms. So we can describe a plane in R3 with a function or an equation. When we write the function, this is the function form that we had. Z naught plus m times x minus x naught plus n times y minus y naught. This is a plane that goes through the point x naught, y naught, and z naught. dz dx is m, and dz dy is n. We ended up with two slopes. We can also write an equation for our plane. Really just we're going to rearrange this and use z, so subtract the z naught and then kind of multiply stuff. So our equation in standard form I guess I wrote the equal 0 version. Here's a plane containing the point x naught, y naught, and z naught. And in this case, the coefficients a, b, and c describe a normal vector. So we're describing this plane as everything perpendicular to the vector a, b, c. This was one way to describe a plane with one vector. Everything perpendicular to the normal vector. The big idea here is that we wanted to use one vector to describe the plane. Questions? Remember what we were doing here. Remember that we came up with it. We introduced this normal vector business when we were talking about vector operations. And we said this normal vector is the cross product of any two vectors in the plane. At the time, we were like, oh, that's kind of inconvenient to describe a plane with two separate vectors. Let's try to describe it with one vector. Let's make one direction for the plane because that's what a linear function should be. In our mind, we're like, oh, that's what a linear function should be. Start here, go this direction. We should be able to describe a plane a linear function, a flat surface with one direction. Problem was, plane is two-dimensional. So what we do is describe it with the normal vector. At the time, that's why we started doing this. That's why we introduced this normal vector business. That was our justification back then. So the normal vector is the cross product of any two vectors in the plane. Remember what we're thinking about here. We're thinking about parameterizing a surface. That means we're going to have two parameters, an S and a T. The other way we can describe the plane, so we started describing planes by any two vectors. Any two lines make a plane, so any two vectors make a plane. A plane is a set of all the linear combinations of any two vectors, of any two non-collinear vectors. So if we take two vectors from the plane, any two non-collinear vectors from the plane, the plane is the span of those two vectors. When we say the span of the set of vectors, that is all linear combinations of those vectors. Weird that I wrote the set after the word of. So the plane that we're describing, the set of the two vectors, u and v, describe a plane. So we could say that that plane is the span of those two vectors, span of a set of vectors. So the abbreviation for that is very cleverly span, and then we just write the set of vectors afterwards. Usually with a capital S, if I recall my linear algebra. So what we mean when we say all the linear combinations of u and v, that means we take every scalar multiple of u and every scalar multiple of v and put them all together. So the linear combinations of U and V is a set of everything that looks like, say, some scalar times U plus some other scalar times V. There are the two parameters that we need to describe the plane. And they were blue. That's what a linear combination of things is. Scalar times one plus a scalar times another. So this goes back to the beginnings of our geometry. We know that 2 points make a line, 2 lines make a plane. This is just some more math surrounding 2 lines make a plane. A plane is the span of 2 vectors. If we're going to describe a plane as the span of 2 vectors, we are using 2 parameters. How much of the first vector plus how much of the second vector. Questions? I know I ask this all the time. I can't remember how many people took linear algebra. Has anybody here taken linear algebra? So when chapter 13 shows up and you're like, oh, vectors, didn't I just do vectors? Like, oh yeah, and we're doing them again. And then in physics 250, didn't you do vectors? Has anybody taken engineering statics? An engineering class called statics? Guess what shows up in statics? Fucking vectors again. Damn it, can I not escape these vectors? Yeah, physics 250. 250 is mechanics, right? And then 260 is electricity and magnetism. And then 270 is like everything else. It's just like calculus. The first 2 are so focused, and then the last one is like, oh, everything else. Crazy. This is because we try to divide calculus into like 3 semesters, and it doesn't really divide by 3. Because you got your limits and continuity, and for whatever reason, we do derivatives first. I don't know why. When it comes to things like this, I tend to blame the English. So it's like, oh, we should have Newton go first. Newton, you should go first because you are English. So we're going to do yours. We'll do your idea of fluxions. All right. How's everybody okay? So if we want to describe a 2-dimensional surface, we need 2 inputs. When we had a function of 2 variables, those were our 2 inputs. It was just slightly different. Our parameters were also acting as coordinates. So we're using 2 coordinates as the parameter. But we can free ourselves from that by installing parameters that sit outside of our coordinates. So instead of deciding that z is a function of x and y being coordinates and also parameters for z, we can install parameters sitting outside of x, y, and z usually S and T in this book anyway. S and T as parameters so that our coordinates X, Y, and Z can be independent of each other. We might also see when we only have two, it makes sense to just give different letter names to things. U and V, S and T, two different names for our parameters. But if you're thinking this might generalize, those students have been through linear algebra know that this totally generalizes. And then we say, well, what if we have more? In which case it makes sense to just use one name for the parameters and another name for the vectors. And then subscripting them. So I can't have kids, I'll just use subscripts for them. Here's your first kid. What are you going to name it? Leech sub 1. And then leech sub 2. And leech sub 3. Then I would legally change my name to leech not. Actually, I totally wouldn't do that. I'm not really a big fan of my last name, so I would never foist that on somebody else. All right, so that's what I wanted to say about parameterizations. The idea with this, these parametric equations is that we write our coordinates as functions of a parameter, and that parameter it should not be one of our coordinates. What we're doing when we write a function y equals f of x is we're using one of the coordinates as a parameter. That's very restrictive, using one of the coordinates as a parameter. And then it's most restrictive when we require that one of the coordinates be a function of the other coordinate. We get a little freedom if we don't require that the coordinates be functions of each other, but related by an equation. We get even more freedom if we can define the coordinates independent of each other as functions of some parameter that sits outside of the coordinates. Any questions? Comments? Deep thought? All right. 10 points for typing F in chat. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.